Hey there. Welcome to ABELE Engineering Guild, your go-to reviewer for the Agricultural and Biosystems Engineering Licensure exam. In this video, we're going over the full solutions to the problems we've tackled in our previous videos from Part 1 to Part 10 under Area 3. So if you've been following along and want to check your answers or understand how to solve each problem step by step, you're in the right place. Ready to dive in? Let's break down the problems, one solution at a time. Okay, for the first problem, it is related to the practical problem in woodworking. Number 1. In a woodworking station, 5 pieces of workbenches are required. According to the engineer's design, each workbench will need 10 pieces of lumber 2 inches by 3 inches by 12 feet, and 6 pieces of lumber 2 inches by 2 inches by 6 feet for each workbench. How many board feet of lumber are needed to build just one workbench? Now, here are your choices. A. 65 board feet. B. 72 board feet. C. 80 board feet. D. 96 board feet. Alright, let's break this down step by step. Given. For one workbench, 10 pieces of lumber with the size 2 inches by 3 inches by 12 feet. And 6 pieces of lumber with the size 2 inches by 2 inches by 6 feet. Required. Find the total board feet of lumber needed for one workbench. Formula. Board foot equals thickness in inches multiplied by width in inches multiplied by length in feet, all divided by 12. Solution. Step 1. For 10 pieces of 2 inches by 3 inches by 12 feet. Board foot per piece equals open parenthesis 2 times 3 times 12 close parenthesis divided by 12. That equals 6 board feet. For 10 pieces, 6 times 10 equals 60 board feet. Next. Step 2. For 6 pieces of 2 inches by 2 inches by 6 feet. Board foot per piece equals open parenthesis 2 times 6 close parenthesis divided by 12. That equals 2 board feet. For 6 pieces, 2 times 6 equals 12 board feet. Finally. Step 3. Total board feet needed for one workbench. For 10 pieces we have 60 board feet and for 10 pieces we have 12 board feet. So, total board feet equals 60 plus 12, which gives us 72 board feet. So, the answer for this question is B, 72 board feet. Next, we go to number 2. Here's the problem. A heat exchanger where oil flows through a pipe with a thermal conductivity of K equals 0.5 watts per meter Kelvin. The pipe has a length of L equals 2 meters and an area of cross-section A equals 0.01 square meter. The oil enters at 80 degrees Celsius and the water enters at 20 degrees Celsius. The temperature difference between the oil and the water is 60 degrees Celsius. Calculate the heat transfer rate. Now, here are the choices. A. 0.10 watts. B. 0.15 watts. C. 0.20 watts. D. 0.25 watts. Now, to better understand our problem, let's take a look at this diagram of a shell and tube heat exchanger. Here's what's happening. One fluid flows inside the tubes, and another fluid flows outside the tubes, through the shell. The two fluids never mix, but heat is transferred across the tube wall. In our problem, we can imagine that the oil is flowing inside the tube. This oil is hot, with an entering temperature of around 80 degrees Celsius. On the other side, we have water flowing through the shell side. The water is cooler, with an entering temperature of 20 degrees Celsius. Now, the pipe wall in between acts like a barrier. It separates the two fluids, but at the same time, it allows heat to flow from the hot side to the cold side. This happens because of conduction through the pipe material. The pipe wall has certain properties. It has a thermal conductivity of 0.5 watts per meter Kelvin. This tells us how well the material can conduct heat. It has a length of 2 meters and a cross-sectional area of 0.01 square meters. And of course, we have a temperature difference of 60 degrees Celsius between the oil and the water, which is the driving force for heat transfer. Given. Let's write down the given data. K equals 0.5 watts per meter Kelvin. L equals 2 meters. A equals 0.01 square meter. Delta T, or the temperature difference, equals 60 kelvins. Required. We are asked to find the heat transfer rate, Q, in watts. Assumptions. 1. We assume steady, one-dimensional conduction through a uniform wall. 2. We assume that material properties are constant. 3. We assume the temperature drop across the wall is 60 Kelvin. 4. And we assume there is no internal heat generation. Formula. The formula is Fourier's law for one-dimensional conduction. Q equals K multiplied by A multiplied by delta T divided by L. Let us now solve the problem. Step 1. Temperature gradient term. Let's find the temperature gradient. Delta T divided by L equals 60 divided by 2. That equals 30 Kelvin per meter. Step 2. Material and area term. Now let's find K times A. That is 0.5 multiplied by 0.01. That equals 0.005 watts meter per Kelvin. Step 3. Multiply them together or compute heat transfer rate. Now multiply 0.005 by 30. That equals 0.15 watts. The correct choice is letter B, 0.15 watts. Think of heat like water flowing through a pipe. The bigger the pipe area, the easier the flow. The longer the pipe, the harder for heat to flow. The hotter the difference, the more heat will move. Here, the answer came out to 0.15 watts, which is a very small amount of heat flow. Next, number 3. Suppose the pipe has a radius r equals 0.05 meters. The thermal conductivity of the pipe material is K equals 0.5 watts per meter Kelvin. The length of the pipe is L equals 2 meters. The temperature of the oil is T1 equals 80 degrees Celsius, while the water enters at T2 equals 20 degrees Celsius. Calculate the heat transfer rate. Choices. A. 0.100 watts. B. 0.118 watts. C. 0.150 watts. D. 0.200 watts. Okay, to make this problem easier to understand, let's imagine a very simple situation. Think of a straight metal pipe, like a hollow tube, that is 2 meters long. The pipe is not too big, it has a radius of 0.05 meters, about the size of a small water bottle. Now, hot oil at 80 degrees Celsius is flowing inside this pipe, while on the outside, cold water is passing by at 20 degrees Celsius. Because the oil is hotter and the water is colder, heat will naturally transfer from the oil, through the pipe wall, and into the water. The material of the pipe itself matters here too. In this case, the pipe is made of a material that has a thermal conductivity of 0.5 watts per meter Kelvin. That number tells us how easily heat can pass through the pipe. So, in short, we have hot oil inside, cold water outside, and heat traveling through the pipe wall. What we want to calculate is the rate of this heat transfer, basically, how much heat per second is moving from the oil to the water through the pipe. Now, let's list down the given values in our problem. First, the radius of the pipe is R equals 0.05 meters. Second, the thermal conductivity of the pipe material is K equals 0.5 watts per meter Kelvin. Third, the length of the pipe is L equals 2 meters. Fourth, the temperature of the oil is T sub 1 equals 80 degrees Celsius. Fifth, the temperature of the water is T sub 2 equals 20 degrees Celsius. And lastly, the temperature difference is delta T equals T sub 1 minus T sub 2, which is 60 Kelvin. Required. Calculate the heat transfer rate. Assumption. We treat the heat flow as steady, one-dimensional, along the pipe, using the cross-sectional area. Formula. Use Fourier's law for axial conduction. Q dot equals K times A times delta T divided by L. Area A equals pi times R squared. Solution, Step 1, area. Compute A equals pi times R squared. That is pi times open parenthesis 0.05 close parenthesis squared. So, A equals 0.0078539.816 square meters. Step 2, temperature gradient. Delta T divided by L equals 60 divided by 2 equals 30 Kelvin per meter. Step 3, multiply. Q dot equals K times A times delta T over L. That is 0.5 times 0.0078539.816 times 30. Gives 0.1178097245 watts. Rounded, Q dot equals 0.118 watts. The correct answer is letter B, 0.118 watts. Here's our next problem. A copper wire is 15 meters long with a cross-sectional area of 2 times 10 to the negative 6 square meters. If copper's resistivity is 1.68 times 10 to the negative 8 ohm meter, what is its resistance? Choices. A. 0.102 ohms. B. 0.120 ohms. C. 0.126 ohms. D. 0.150 ohms. Let's list the given values. The length of the wire, L, equals 15 meters. The cross-sectional area, A, equals 2 times 10 to the negative 6 square meters. The resistivity of copper, ρ, equals 1.68 times 10 to the negative 8 ohm meter. We are required to find the resistance of the copper wire, which we'll denote as R. The formula for resistance is R equals resistivity, ρ, multiplied by the length, L, divided by the cross-sectional area, A. Now substitute the values. R equals 1.68 times 10 to the negative 8, multiplied by 15, divided by 2 times 10 to the negative 6. Plug in all the values to your calculator, you'll get 0.126. Looking at our choices, the correct answer is letter C, 0.126 ohms. Imagine you have a very long phone charging cable, let's say 15 meters long. Just like in our problem, the wire inside that cable is copper. Now, when electricity flows through a wire, the wire itself slows it down a little. This slowing effect is called resistance. The longer and thinner the wire is, the more resistance it has, kind of like how water flowing through a long, narrow straw becomes harder to suck through compared to a short, wide straw. In our case, the copper wire is fairly thin, with a cross-sectional area of only 2 times 10 to the negative 6 square meters. Even though copper is a good conductor with very low resistivity, 1.68 times 10 to the negative 8 ohm meter, it still offers some resistance because of its length. When we calculated, we found the resistance is 0.126 ohms. That's a small value, but over a very long cable, it can actually affect how efficiently your device charges or how much energy is lost as heat. So, this is why electricians and engineers carefully choose the thickness and material of wires. Thicker wires mean less resistance and better current flow, just like using a big straw makes it easier to drink your juice. Problem number 5. Shrimp harvested in a pond situated in Bohol are packed in insulated sheet metal containers and mixed with crushed ice while in transit to the shrimp processing plant in Manila. Initial temperature of the product is about 25 degrees Celsius and it is desired to cool the shrimp at approximately 0 degrees Celsius during shipment. Estimate the product load, in kilojoules per kilogram. For shrimp, the highest freezing temperature is negative 2.2 degrees Celsius, Cp above freezing is 3.38 kilojoules per kilogram per Kelvin, Cp below freezing is 1.79 kilojoules per kilogram per Kelvin, and latent heat of fusion is 254 kilojoules per kilogram. Choices. Letter A, 98.2 kilojoules per kilogram. Letter B, 84.5 kilojoules per kilogram. Letter C, 72.1 kilojoules per kilogram. Letter D, 68.3 kilojoules per kilogram. In this problem, we are tasked to estimate the product load of shrimp during shipment. The situation is this. Shrimp harvested in Bohol are packed in insulated sheet metal containers and mixed with crushed ice, while in transit to Manila. The initial temperature of the shrimp is about 25 degrees Celsius, and it is desired to cool them down to approximately 0 degrees Celsius during shipment. So, let's write down the given values. The initial temperature is 25 degrees Celsius. The final temperature is 0 degrees Celsius. The freezing temperature is negative 2.2 degrees Celsius. The specific heat above freezing is 3.38 kilojoules per kilogram per Kelvin. The specific heat below freezing is 1.79 kilojoules per kilogram per Kelvin. The latent heat of fusion is 254 kilojoules per kilogram. Now, for the required. We need to determine the product load, Q, in kilojoules per kilogram. Since the shrimp are only cooled from 25 degrees Celsius down to 0 degrees Celsius, and not all the way to the freezing point of negative 2.2 degrees Celsius, there will be no phase change and therefore we do not include latent heat in the calculation. So, we only consider the sensible heat above freezing. The formula is stated as: the product load is equal to the specific heat above freezing multiplied by the difference between the initial temperature and the final temperature. Now, let's substitute the values into the formula. The product load is equal to 3.38 multiplied by the difference between 25 and 0. Simplifying inside the parentheses, 25 minus 0 is equal to 25. So, the product load is equal to 3.38 multiplied by 25. Therefore, the product load is 84.5 kilojoules per kilogram. Imagine this, melting ice cream on a hot day. You just bought a tub of ice cream from the store. It is a hot day, about 25 degrees Celsius, and you are walking home. But you forgot your insulated bag, so you are just carrying the ice cream in its regular container. Now, you want to keep the ice cream from melting before you get home. So you grab a cooler box and fill it with crushed ice, hoping it will keep the ice cream cold. Here is the catch: the ice cream starts off at 25 degrees Celsius, just like the shrimp in the original problem. But to keep it from melting, you need to cool it down to 0 degrees Celsius, the temperature where it is safe and solid. So, just like with the shrimp, you are asking the ice to absorb heat from the ice cream to cool it down. That is your product load, how much heat energy needs to be removed per kilogram of ice cream. You did not freeze it solid, so you do not need to worry about the latent heat, the energy needed to change it from liquid to solid. You are just cooling it down, like putting it in the fridge, not the freezer. And that's it for today's problem. If you learned something new, make sure to like this video, subscribe to ABELE Engineering Guild, and hit the notification bell so you won't miss the next update. This video is part of a series, so watch out for the next update. Thanks for watching, and see you in the next video.